In this video, we will use the ice table to determine the final equilibrium concentrations of CO, H2O, CO2, and H2 after this reaction achieves equilibrium. So the way to actually do this problem, there's some key words here. One is the key word is initially. So initially is different than finally, right? So initially we have this moles over liters of H2 and this moles over liters of CO2. And we want to figure out when this reaction is all complete and done and does its business, what is left? What is left in terms of this, and these two reactants. Now remember, in equilibrium, you're going to have reactants left over as well as products. So if they're equal in their concentrations, then the equilibrium constant is 1. But if they're unequal, then one side will be favored versus the other side. Either products will be favored or the reactants will be favored. So initially tells me that I got to use the ice table. Initial, change, and equilibrium. First of all, it's concentrations, right? So what goes into the ice tables are concentrations. So we're going to have to take this mole and divide it by that liters to get our concentration. So 0.080 divided by 5 is our concentration of H2, as well as the same thing for our concentration of CO2. So I went ahead and did that here. This is an inventory of all that we have in our problem. And now we're going to do our ice table here. So initially we have 0.16. So let's just fill out our ice table here, ICE. Initially we have 0.16 of H2 gas, 0.16 of CO2 gas. This is what's just been started. And we're going to say we have 0 of this and 0 of that. So the change is going to be minus x, because it's 1 mole. So minus x would mean minus 1 mole, minus 1 mole. 1 mole of H2O would make this plus x. 1 mole of CO, carbon monoxide, will make this plus x. So at equilibrium, we will have 0.16 minus x, 0.16 minus x, plus x, and plus x. Okay, our job is to find x, plug it back in to get our final equilibrium concentrations. So what is our equilibrium expression? Our equilibrium expression is going to be products over reactants. Is here x. I guess I'll do the simplification a little bit later. And H2 and CO2 are both 0.16 minus x. So hopefully you can see that this is nothing more than x squared divided by 0.16 minus x, that whole thing squared. Okay, that is equal to, that has to equal, when this gets into equilibrium, that has to equal to 4.2. Remember, it's quoted at a specific temperature. So this has to equal to 4.2. Let's go ahead and take the square root of both sides of the equation. Equals the square root of this whole thing, x squared. Square root of x squared is x, and 0.16 minus x whole square. The square root of that is just 0.16 minus x. So square root of 4.2. So let's do that quickly on our calculator. Let's just say 2.049. Let's just put in some extra digits here when we solve for x. And this is going to equal to x divided by 0.16 minus x. All right, so let's solve for x here, isolate that, and then when we solve for x, we got to plug it back in here. Okay. So I'm going to multiply both sides by 0.16 minus x to bring it in here to x. So we have here 2.049 times 0.16, that's the distributive property. So times, so that's going to be 0.3279 minus 2.049x, and that has to equal to x. So let's take this minus 2.049, bring it to the other side. So that's 1x, 1 plus, to get to the other side, 1 plus 2.049 is 3.049x, and that has to equal to 0.3279. So we can isolate x here as nothing more than 0.3279 divided by 3.049. So doing that on my calculator, concentration, but that's not our final concentration, right? Our final concentration at equilibrium is taking this and then plugging it all the way back up to our equilibrium values in the ice table. All right, so Our final concentration is this. Let's plug it back in here. So the equilibrium concentration of H2, let's write that on the side here, is going to be 0.16 minus x, but we already found x, so it's 0.16 minus 0.108. 052, now here you want to put the units. It's going to be the same thing for CO2. Okay, we're plugging this back in here. So CO2 is going to be the same thing, 0.16 minus x. And then our products are x and x. Well, we already found x as 0.108. So these would be our concentrations at equilibrium. So these are our equilibrium concentrations. Let me show you a way that you can cross-check your answer to make sure on the exam that you are truly having the right answer. And that is plugging these equilibrium concentrations back to the equilibrium expression. And they tell us that the equilibrium constant Kc is about 4.2. So what is our equilibrium constant equal to? Well, it's equal to the equilibrium expression, products over reactants. So the equilibrium constant in terms of concentration is products, H2O times CO, okay, raised to the 1 power, divided by the concentration of the reactants, each raised to the 1 power, so that's H2 and CO2. Okay, they tell us, so the goal here is we're just trying to make sure we have the right answer. They tell us at this temperature, it's 4.2 is our equilibrium constant, and H2O and CO at equilibrium are 0.108. So that's going to be 0.108 squared divided by H2 and CO2 at equilibrium are both 0.052. So 0.052 times 0.052 is 0.052 squared. So does this equal to 4.2? And if it does, we know that these are the correct equilibrium concentrations. So 0.108 squared divided by 0.052 squared, and 4.3, I think that's going to be close enough. 4.2, we got a value of 4.3. I think that's good enough for us to, at least with some reasonable bit of confidence, say that these are the right equilibrium concentrations for this reaction. So in other words, there is a way to check to make sure your answer is correct.